Okay, so the goal is that somehow you want to move the bits from 3G. 3G is a representative, expensive, controlled, managed network, Wi-Fi, free license, free open access sort of network, to primarily save cost. And there are other things that will come up a little later. And the context we are doing this is, I mean, we all of us do that all the time. We prefer obviously over Wi-Fi over 3G, at least for performance. But the context here is moving vehicles. Okay, and why moving vehicles? Because that is a challenging part of it. And after all, I'm a professor working in academia, so we're trying to focus on the most challenging aspect of the problem. And it has been a lot of fun doing this. And we have been doing this sort of thing, not involving 3G, but just focusing on vehicular Wi-Fi for the last several years. Now, this talk, what I'm going to say a little bit about why we are doing it, okay, some context. Second is that it's practical, really makes sense. Okay, of course, we are going to say it's practical. I'll show you some numbers, some measurements that we have done, how we are going to do it, it's important, and there's some real experience. And big twist here, relative to what other works, many other universities are doing, is that the Wi-Fi that we are selecting now is a metro Wi-Fi, a huge deployment of Optimum WiFi in London. Also, you can see those in the Rutgers area in New Jersey. And that gives us a flavor of some sort of reality. So we can really drive over a wide area with varying traffic conditions and look at the performance. And some usage scenarios, because we need to motivate this, that what type of things you can do in a car. Of course, lots of things you can do. You can try home after work. You can download an evening broadcast, for example. The kids at the back seat can stream a video clip. Okay. Increasingly becoming popular. Also, you can do some little bit simpler stuff like download, upload, traffic, weather. It cannot be a very high volume of data, sensor data, looking at vehicles and mobile sensor. That sort of things is becoming popular. So those things you can do. So I'm avoiding talking about anything which is sort of real time, like interactive communication with audio or video. It's not very clear how that will play out in our context. But anything that is sort of elastic traffic, okay, and that's the type of traffic we are focusing on. Now, why? Okay, so of course should be obvious to all of you here. 3G is licensed spectrum. It's expensive. Somebody is paying for it, directly or indirectly. And also you can see that there is already a recent move from flat rate pricing to tiered pricing in some US-based providers, like AT&T recently announced that. So that means the fees are costing them, and you better pay for them. It's important. Also, there are a lot of anecdotal evidence, particularly if you follow the stories with AT&T and iPhone, you know that some networks are already won the, particularly in this tri-state area, AT&T's network. Due to heavy volume of smartphone traffic, everybody is like watching YouTube or iPhone, for example. So they don't really have capacity. It may be part of their problem, part of the spectrum problem. It's hard to know what type of problem it is, but the user experience has been poor. Also, so we can easily move these bits to Wi-Fi, because all the mobiles that you see in the smartphone spectrum, netbook, and iPad, and all these devices, they already come with both interfaces. So it's not very hard thing to do in general. The hardware is already there. These are, I just put up on these slides about differences just to bring ourselves to the same page. There's nothing new here that you don't know. 3G is vertically managed, well planned, almost perfect coverage. This is good. It can even provide some sort of quality of service if they manage it well. It's not very clear how well they do that, but it's possible for them to do that. They can schedule traffic. They can do very nice frequency planning, stuff like that. They can even do admission control if they want to. But the maximum bit rate with the current technology is lower than Wi-Fi. Of course, you go to 4G and other things. Wi-Fi is also getting better. There are a lot of high rate standards. But in general, we prefer Wi-Fi because of better rates. That has been our common experience. Wi-Fi is, of course, very different. It's primarily meant for indoors. That's the way the 5 layer has been structured. Handoff is managed. It doesn't work very well with high mobility. And we are essentially trying to take an indoor technology which has been widely successful and putting it outdoors again. Okay. doing some engineering. Outer coverage, on the other hand, is poor. There are not so many deployments. But getting better with this metro Wi-Fi, that's why I'm focusing my attention there, because there's already very nice networks, at least certain parts of the world, not everywhere. But there are lots of problems. No quality of service of any sort is possible because the spectrum is free. Anybody can do whatever they like, pretty much. Deployment is chaotic, less planned than 3G at least. But the good thing is that it's commodity. It is cheap. It is everywhere. Even your camera has it, your printer has it, your SD card has it. So everything has a Wi-Fi interface. And also for providers, for that same reason, there's a low barrier to entry. You can put up a carrier-grade access point at a very low cost, really. So people can deploy these networks pretty easily related to 3G. Now, you may ask that why we are just concerned so much about 3G and Wi-Fi, really. Why I'm not talking about other things. For example, why not LP, WiMAX, in this licensed spectrum domain? Why talk about Wi-Fi? Maybe why not about white space sort of stuff that is coming up? And also, the type of argument I'm trying to make that one is expensive or that is cheap, this is going to really play out in the future. Okay, because all these new emerging spectrum licensing rules, people are writing lots of papers in dynamic spectrum. Maybe there will be a secondary market for spectrum, and people are going to divide and share the spectrum in new ways. So all these things that we are trying to do now is not going to hold water, in future, because spectrum license might itself be cheap. So I don't know the answer, so I put some dots here. Okay, so it's very difficult to see this sort of future. At this time, we are doing it because it seems like it's not only fun thing to do, it's a very useful thing to do because the hardware and networks are out there already. And so it is interesting to study feasibility. That's important, whether it actually works in a real-life scenario. And then maybe it can drive some new business models. I have not really focused on this business model part of it, but that is something that we want to do maybe in the future, talking to providers to see whether they're interested in this. Now, is it feasible, really? Okay. Now, there has been lots of papers, including our own and some of your papers from the lab also came out in the last couple of years. It started maybe 5 or 6 years back, a little longer than that, from a paper that appeared in Infocom called Drive to Internet from University of Bremen in Germany. They tried to do vehicular Wi-Fi and got some good results. Then there was a lot of work by MIT in the Cartel project, and we followed it up. Then there is the UMass, Rutgers, Microsoft Research has done a lot of work, ABC Labs, Wisconsin. So there has been lots of projects trying to access Wi-Fi. Vanilla Wi-Fi, we are not talking about DSRC or other type of high layer, the regular .11b, for example, mostly .11b. And but all these projects mostly use open APs in urban areas. They are open. Campus AP deployments, or sometimes like much of our work was self-deployed APs because we had to put certain functionality on the AP. Okay, so you cannot really use other people's APs. You have to deploy our own. That sort of limits the type of results you can get because how many APs you are going to deploy on yourselves? Not many really. So all this research showed that vehicular Wi-Fi is feasible, but there are lots of problems. Okay, particularly frequent disconnections, coverage holes. These are basically coverage issues. Not so much you can do on the client side, but handoff and link quality and that sort of stuff. There are lots of technical solutions for those. But in this whole, this sort of work is getting increasingly impractical, and we kind of realize this because we did this for a while, trying to access open APIs. Because the number of open APIs are reducing. Everybody is security conscious, so most of the APIs you cannot really access. And also, it's not very clear whether you should be accessing open APIs, even if they are open. So there could be legal issues. And that much of the networking community didn't realize this until recently. On the other hand, it appears to us that there's a little experience in studying metro Wi-Fi deployment for vehicular Wi-Fi access. So that is the sort of the new twist in our work. Now, to do anything at all, what you would normally do in this space is that you will take a lot of measurement data. Much of the things I'm going to talk about is basically measurement. That we do something very simple, that take two networks, which are sort of obvious choices in this region, in Long Island particularly. The Verizon's EVDO railway network, which is the best 3G probably. Very few people will disagree with this in Long Island. T-Mobile, Sprint, AT&T doesn't work that well. It's a normal experience. And then there is this deployment of Optimum Wi-Fi, and many of you would be familiar with this as well because I see the deployment in New Jersey from the same provider. And this is on a local ISP, and they did this probably maybe a couple of years back, and there's a lot of APs really. Their web page has 18,000 APs in Long Island, plus some portions of the New York City, Connecticut, New Jersey, and Pennsylvania. And I was trying to show you a picture from their web page. So this is like all these APs. It doesn't show very well on this screen, but if you look at that on the computer, it will be better. All these little dots are they're showing the coverage of their outdoor APs. These things are there indoors. So it's a lot of deployment outdoors. And if you just scan this map, you can see this is JFK Airport down below, and there is no deployment there. But if you again come to like Queens area, there is a huge amount of deployment. And if you go a little bit towards east, there's a lot. So of course the density sort of varies. Near Stony Brook, they are not that much, but most of the island is covered one way or the other. Particularly where people live, the more densely populated areas. There are deployments around Rutgers, and when I was on the train, Wi-Fi APs were popping up occasionally. So this is substantial deployment. They claim this is the largest Wi-Fi in the nation. I don't know whether that is true, but this is a good network test. So that's what exactly we do. We actually took Linux laptop, and we have cars. And students drive around to collect data. And the laptop has two network interfaces. One is a USB modem for the 3G, which is the same modem I'm using on my laptop. And then for the Wi-Fi, it's a little tricky. Okay. And so here, we probably are doing something that cannot be done on a real mobile. It can be done in a car. We had to use a carrier-grade PCI interface, the Ubiquiti product, and we fixed transmit power. We had to use a very high gain antenna, omnidirectional antenna, 12 dBi, that gives a very low particle beam width. And for some reason, these antenna had to be used, otherwise nothing really worked very well. If you use the lower gain, and that will give higher particle beam width, you would normally think that the larger particle beam width will be better because there will be more opportunity for it to capture APs. But for some reason, this antenna works very well. And one of our explanation is that what you can do here is that with a high gain, even though the particle beam is small, maybe you are getting associated with a very distant AP and remain associated with that for a very long time. Okay, so probably you are not connected to something very nearby. Yes.
And the antenna is actually on the car; it's not on the roof.
It is on the, okay, so yeah. These sort of antennas are very like, it's a kind of long stick. It's a very long, okay, like this. Okay. So the car has a sunroof, and then the computer is inside the car, and the antenna sticks out. So it's not really outside, the part of it is inside, part of it is outside. That's that.
Because I wonder then how fair is the comparison, because then is 3G antenna also mounted on the roof?
No, 3G antenna is not mounted upstairs. Yeah, there can be little issues there that the antenna is outside, on the other hand, 3G is inside the car. Okay. Actually, maybe you should do something like this. Maybe you should stick the 3G antenna, 3G card itself via USB cable outside. That we didn't think about. It is true that there are things that can be done to make the comparison, but they are completely two different networks. But whatever is coming out from here still is highly extracted. And we have GPS to log locations because we have to study location tracks. Now we drove around a lot. This drive is very realistic. So you just drive with traffic. There are many hours of driving, and there's still driving so that we get more mature data. And then we do continuous TCP downloads on both interfaces. Now, for Wi-Fi, there are many things that can go wrong, really. Because, of course, one of the things that go wrong is that how do you do handoff? We really don't control the handoff, even though we did a lot of handoff related research before, trying to optimize handoffs. We didn't really do anything here. We just let the default driver select APs and the handoff. And IP address, interestingly, is retained across handoff in this network. So I don't really have to get a new IP address. Because otherwise, if I have to get a new IP address, then naturally things will be very slow. Okay, and that is completely going to beat the performance. That doesn't happen on the Wi-Fi. It probably happens occasionally, but not frequently enough to impact performance. And then there are problems with mobile TCP because we focused on TCP traffic because it's the predominant traffic. There are problems with mobile TCP, maybe if you were aware of that, because if you get disconnected, that happens in Wi-Fi, and then get reconnected again, the retransmission back off, that timer becomes very large, and that can impact adversely the performance. We actually did some ad hoc solutions to fix this. It's not the best of the solutions. It's not one of the literature standard solutions. But it's just that we did something that works well. Things can be improved further, and one of the things that we have to do is to improve this. So things can only get better here. It's not going to get worse. That is the message. No, we did not have the perfect solution. Now, given the scenario, in a driving situation, this is what we get. And this is about 40 to 50 hours worth of driving. We have more data. It sort of depends also exactly where you're driving. This is one of the best parts of coverage, in the sense of the coverage. Okay, of course, the coverage could be weaker, and the coverage density varies. But we chose in this particular plot to drive about 40 hours work to drive in regions where the coverage is better. And there are two different types of drive, short and long. Don't worry about this. This long drive is just random drives. Short drive is the drive that you're repeating. That doesn't really, it's not a significant difference. So if you look at the CDF of instantaneous throughput, then you'll see that there are some things interesting coming out. That, for example, so the 3G curve is sort of smooth, and the median throughput is much smaller. Okay. Wi-Fi media is about 3 times more. But Wi-Fi exhibits something interesting that if you look at the Wi-Fi, there are kind of 3 modes. One mode is here, where you don't get any throughput at all. Okay. Probably there is no coverage, even if there is coverage, you couldn't really connect because of vehicle speed, for example. Okay. And which is expected. And then the other part at the top is a very high throughput. Okay, relative to 3G, for example, is 2.5 megabit per second, which is probably, and you'll see later, it's probably areas where you have a good coverage and you're probably stopping or driving slowly. Yes?
Can I ask how do you determine the instantaneous throughput?
Okay, so actually, you measure the throughput every second.
Every second through cycle, or?
Yeah, I don't think we use DIPER. I believe they use their own custom tools, and then the log the throughput. So every second, we have a meter of throughput. That is instantaneous.
Because you don't control the Wi-Fi, right? So what's the other endpoint of who is transmitting data for the other side?
It is download. It is download from the server. So you connect to a server in WINLAB, okay, and it's only download from the server.
Okay.
Okay. So it is the received throughput at the point.
But this also captures the background. I mean, the whatever backbone connectivity each of the networks.
Yes, true. Yeah.
So you're not sure whether this is due
This
to
is why, yeah, this is the
rise of
standard.
that
Yeah, we don't know that. It could be Verizon backbone or universal backbone.
Exactly.
It's everything. It's like end-to-end throughput. Yeah. It is not from the access point because we don't have any access to access control. Yes.
And then are you doing the download simultaneously on both?
Yes. And we made sure before by doing that the computer speed itself, the laptop speed itself is not playing any role. We made sure that it's not playing any role here. The laptop is firing 2 different connections at the same time. Yeah. So this is at the same time both are working. So this is instructive. It seems like Wi-Fi, if it works probably very well. If it doesn't work at all. Okay, so which is kind of an interesting insight. Now, yes.
Wi-Fi device and 3G device are located in the same location,
Yes.
right? Or
Yes, it's the same location, but as I pointed out to the previous question, is that there is a little difference in the antenna in the sense that the Wi-Fi is 3G antenna is in the car because it's a little thing. Okay? We didn't really take it out. The Wi-Fi antenna is long, so it starts from the car but sticks out because it's longer than the
maybe
higher.
with Wi-Fi you have always a line of sight. With 3G you don't have a line of sight, therefore you have shifting.
Possible. Actually, this is something we didn't think of very carefully. Maybe there's a good point, but I need to make sure the students repeat of this to see whether there's any variation in 3G throughput if I put the 3G card on the roof of the car, for example. So,
I doubt it's going to change because I think there is a high probability that Verizon's backbone is somewhat limited. It's going to be interesting.
could be. I don't know. But,
Yeah,
but it is, I mean, why Verizon's backbone will be limiting and not Wi-Fi, Optimum Wi-Fi's backbone.
Because of, keep in mind that most 3G sites are still powered by T1.
Okay.
Right. And T1 is one.
So you are saying that it is a part of the reasons of all these things is the backbone, not so much the wireless. Good. Yes.
So just to add on to Ivan's point, right, one thing about 3G is that there's very few gateways into the backbones. So it might actually get routed like all the way to Michigan or somewhere before it comes back.
Yeah, I noticed that.
So
by recruiting,
I actually have a suggestion here. Try doing UDP because that is not subjected to latency as much as TCP is.
We did the UDP as well. I'm showing you the TCP data. That we did not do UDP as much as we did TCP. We have much more volume of data for TCP. But it didn't really change, the general nature didn't change very much. But I mean, I don't.
No, but I mean, those two the same. Those two the same.
But why the routes will depend on TCP or UDP?
No, they won't. So that's why they won't.
But you are talking about latency means this first of latency impacts TCP more.
Correct, because UDP you can just blast to get the throughput instead of waiting for TCP to ramp up.
True, but on the other hand, if you look at traffic, people are going to, even people stream videos, they'll use TCP. TCP is so much important for people. So at the end, we are going to focus on user experience. So I understand your point, because it may be that the difference get bumped up because of TCP. Okay, maybe it's not getting that much of a difference. But I didn't see that much difference when you do UDP. Okay. Speed. I think if you were there in the WINLAB meeting last time, Varuna from UMass gave a talk, a similar sort of thing, even though our techniques were a little different. And the speed question came up, and we did evaluate the speed carefully. We quite expected that speed impacts performance. And interestingly, it didn't impact. So this is like I classify the speed slow, medium, and fast. And look at the 3G plots. If you ignore this little difference, it doesn't change very much in speed. There is some difference, but not that much. Wi-Fi is wildly different. Okay, particularly if you're slow, okay, things are very good. And if you're fast, things can be very poor, which is probably due to handoff situation. We sort of anticipate that and validates this. But on the other hand, I must say in our defense that this is just normal driving in Long Island in afternoons and evenings, a lot of traffic. So this is your actual experience. If it is slow, then the traffic is, what can we do?
So you think the Wi-Fi working better at slow speed, you said it's something to do with, you said with handoff, if you want 3G, if you want handoff. So why does Wi-Fi vary with the speed?
Okay, so the reason is that Wi-Fi handoffs are not optimized very well, right? So handoff takes time because you have to go through a device discovery, AP discovery. So if you don't hand off frequently, the performance will be better.
So then why do you, I'm confused by your graph, that it seems like your graph is so fast, isn't it?
Slow is better.
Slow is better. Slow is better.
Oh, okay, I don't understand.
Okay.
Is that curve lower?
It's lower because there's a bigger fraction of time you have a higher throughput. Yeah. I suspect it could be a little bit related to the fading type of stuff related to file layer, but I suspect more, it is the slow is working better because of handoffs. Handoffs are less frequent. Okay. But there is no handoff at all because you are waiting in the traffic. And that situation is also covered.
That's perfect.
Yeah, if you're stopping. Now, here is a head-to-head comparison. So previously I was showing just and a PDF, CDF of individual networks. Here it is head-to-head. That means at the same instant, by instant I mean 1 second. Okay. So what is the performance differential between Wi-Fi and 3G? Okay. So this is Wi-Fi minus 3G. Okay. So it's negative means Wi-Fi is poorer and 3G is better. It's positive means Wi-Fi is better. And 55% times Wi-Fi is better, and sometimes it can be significantly better. And 45% of the times 3G is better. But it cannot become very significantly better. So if you look at the car, there's like more weight on the other side in some way or another. And it also is true because we already sort of showed that about 1/3 of the time you probably cannot connect to Wi-Fi or don't get anything. So it looks like 3G is better. Maybe around 8 or 10% of the time, both networks are operational, but 3G is giving you better throughput. But the rest of the times, maybe Wi-Fi doesn't have connectivity. But once again, you have to take all these measurements with a grain of salt because it's heavily dependent on the deployment. Okay, so very dense things can be very different. Because sparse with Wi-Fi cannot make much sense at all. Measured autocorrelation. It looks like there is very good, probably reasonable correlation both networks. The autocorrelation and Wi-Fi gets poorer as the lag increases. This is the lag, and this is the correlation. It probably is not that important because we will do some scheduling later on, and we just need to figure out whether there is a good correlation with small lags. And in both networks, they are pretty good. It's not clear to me why the autocorrelation and small lag in 3G will be poor relative to Wi-Fi, but that is the result we got. We asked us to verify this many times, but somehow or other, that's what we are getting. But at the bigger lags, Wi-Fi is much poorer. But probably it's not very relevant. Now, coming to the second part of the talk, we have much more analysis of stability, location-specific stability, and stuff like that. But if you are interested, I can give you a draft of a paper that has all these results, and there will be a little more coming up in the next month. Now, let's go to the next part of the talk. So, how would you use this information that you gathered? How to move traffic? So, okay, one thing you can do is something very simple. That when Wi-Fi is available, use Wi-Fi, otherwise use 3G. Okay, so that you can leverage Wi-Fi. This is simple to do and maybe quite meaningful. Okay, but Wi-Fi can occasionally give, even though it is there, you can connect. It's poor, insufficient throughput. We have seen that. Maybe we can take advantage of this observation and try to do a better design, much more robust design. The design I'm promoting here at this time is this formulation based on utility and cost. Okay, so use some idea of network utility function and see whether we can come up with a little more robust modeling, which could be applied to other type of networks. Okay, so what is the modeling? So let's pay attention to the right side of this text here. So let's assume that there is a model of network utility versus throughput. Okay. And in our work, we assume this logarithmic utility model, assuming elastic sort of traffic. But the technique really doesn't depend on how you model the utility. Okay, it can even be application dependent. Okay, so but you have to formulate a utility function somehow, and maybe logarithmic or elastic traffic. Most traffic is elastic is going to work well, but this is up to you. And let's think of this as so that means that the higher the throughput is initially, it is you are happier, but as throughput increases, you are still happier but less so, okay, because you are already getting a lot of miles from the network for your application. And now think about the cost. Okay, the cost also is dependent on throughput because you are putting in more bits in some way. So let's assume there is a fixed cost for Wi-Fi. Okay, and assume some sort of a linear cost of 3G. The more the throughput is, the more bits you are putting in some fashion, and the cost increases. Now, once again, the technique generally is not dependent on exactly how to model the cost. It could be tiered cost or some other way of modeling the cost, but that could be it's just an approach. And this is not a sort of a new approach. Many ways of modeling utility and cost. People have proposed before that, well, one way to optimize the network is that take the difference, that is your benefit. Okay, that is the utility is the mileage you are deriving from the network, cost is something you are paying, in this particular case, some sort of a dollar. It could be other models of the cost like energy. We have some plans of doing that as well. And the difference is the benefit, and you should operate the network at that point where it maximizes the benefit. So once you know all your numbers, you can figure out the correct optimal point. And once you figure out what the optimal point is, you know what type of throughput you should sort of push through the network. And then you need to figure out how much of that you should put on 3G and how much you go to Wi-Fi. Okay. Now this can be formulated. It's not very complicated. And the optimization problem can be solved, which is not complicated either. And I am not solving the math because it's relatively straightforward, but it could be still distracting. You have to introduce notations. So, but the results are intuitive. Okay, so the intuitive results would be, and which you can figure out even without thinking of any mathematical formulation of this problem, is that the way you are going to optimize is that you'll saturate the Wi-Fi, okay, because Wi-Fi is constant cost as much as you can push. And if you still need to push more data to get to the optimal point, you'll put that on 3G network. Okay. And so your cost is going to increase. Okay. The optimal point would have been reached even before just by using 3G Wi-Fi alone. If the Wi-Fi has a lot of throughput. Otherwise, to fill in that slack, you will push that to 3G. So that is basically the strategy. You use the whatever Wi-Fi can take. And if it is insufficient, based on your modeling, then the rest you push on 3G. So essentially, what you have to do, you have to throttle really on the 3G part. Wi-Fi part you don't have to do. Okay. You have to throttle the 3G part, and you can develop now. So a lot of software work for our students to do scheduler, okay, on the sender side, which is the server side, to do the schedule. Okay. And that's what we have done. And this is actually an ongoing work. There's a lot of ways, once again, to develop the scheduler. So we thought about it a lot, talked to a lot of people, and eventually decided that we'll work on a CTP-based scheduler. It's a CTP, yes.
So what's the CTP meaning? The slope of the linear cost? How do you decide that?
This will depend on actual cost that provider will specify. That is basically in some way cost per bit. So,
Is that throughput X on the X-axis like an instantaneous throughput? Like, is it the instantaneous available bit rate, or what is it?
Yes. Yes. You probably have something else in mind.
No, I just, yeah.
So why?
Okay, so this is just an example, and the idea basically is that if you push in more bits per unit time, you are paying more to use the network. Okay, so that's
Pricing.
part of pricing.
So somehow your utility is measured in the units of time. Like you get a drop of utility per second, but the cost is higher if you get more bits. Somehow. Or is it that the all right, maybe I'll go offline and think about it.
Okay. Okay, so we are talking about the scheduler. So there is a, yes.
So given that the cost for the 3G part is linear, is there a range of throughput values where it's just cheaper to use 3G alone because the price point for 3G is lower than the fixed price?
Okay, so there will be a constant cost for 3G. So the model is that there's a constant cost plus linear.
And the constant cost is higher than the Wi-Fi cost. The Wi-Fi fixed cost.
It just depends on your cost. So there is
because depending on whether or not that's true, you might have low throughput applications which will just use 3G periodic updates.
there is okay. So this constant cost you are paying anyways, even if you don't get any throughput, it's a cost you are always paying. So okay. You'll always.
So I think I know what's confused me. We said max Wi-Fi throughput.
Yes.
And I think, well, wait, Wi-Fi is a high throughput thing. That number should be the farthest thing to the right, because you'll never get 3G throughput anywhere near max Wi-Fi throughput.
No, that's not what it is. So basically, from the application, you are, when you solve the optimization, you are determining that there is a specific throughput you want. Now this is the split between the throughput between these two networks. So if you can cover that throughput by Wi-Fi, then you know that's Wi-Fi.
That's the
You
cost
cannot
of
cover.
It's a cost.
That's only the cost.
Right?
I'm just looking at what's a label for plenary access. What's it mean?
These
Max
ones?
Wi-Fi throughput with an arrow.
This is the part of throughput that you are actually putting on the Wi-Fi network. Okay. Now, if this XW is less than, so so this is the part of throughput you are going to put on the Wi-Fi network. If the throughput you need is more than the maximum, maybe the labeling is something a little confusing. The throughput you need is more than the what Wi-Fi can provide, then the rest you put in on the 3G.
Is that in like an average sense, like over
Some
a day or a
intervals.
week or a month?
No. On that instant, in the intervals that you are doing this scheduling for.
So I think
It's
the
just 1 second
point of
interval.
a red curve moves as you go, right? And your cost on Wi-Fi doesn't change. It's just that you cannot push more traffic because you're far away from the destination, well, access point, right? And so if your impression is all the way to the left, that means that you only can put some small fraction of throughput in the Wi-Fi, the rest has to go on the, right? And your max benefit will change based on where that is instantaneously, right?
Okay, so are there other instances and other physical situations where the blue max one, that will be a big
All the way to the
All the
left,
way
right?
there,
Yes.
then you don't have to.
You don't have to do anything on the
You don't have to put any traffic on 3G.
And
Okay.
yeah, of course, then you have a huge benefit, right? I mean, that's how I
So
understand.
so basically this is a situation where you're just really far from a Wi-Fi access point.
Yes.
And it would
Yeah,
be-
then you have to go
You
there.
have to go to 3G. Okay, so we are developing the scheduler and not much to report. However, we did some amount of experiments recently with the scheduler that is an application layer. Okay, so that basically means that there are actually two different TCP connections you open, and then you do scheduling in an application layer on these two TCP connections. And there are a lot of other details here how you build this, because there has to be some error recovery. Since you're using two different connections without any coordination, what would happen is that the Wi-Fi can get disconnected for a long time, and if you have to resequence, because it's basically one single application that is running, and you have to eventually resequence the data on the other end. So if somehow Wi-Fi is late because of the long disconnection, then you probably should do something. Maybe retransmit on 3G or something like that. So we did some ad hoc mechanisms for error recovery, which is not very clean. But once again, it is important to show the potential, because once you make it a clean and better, robust model, robust system, then things can only get better. And that is part of these things are going to automatically come from SCTP. But we don't really have any results on SCTP yet.
Aren't you just running TCP on both interfaces?
Yes.
So that's why is a separate error recovery mechanism needed?
Okay, so it is, of course, the independent TCP is going to retransmit, but the trouble is that suppose the Wi-Fi connection is disconnected for some time. That can happen, really, right? So eventually, when the connectivity is back, then you will retransmit this data. Okay, but what happens is that if the disconnection is long, then nothing is going to work, because the application on the other end will be expecting this piece of data. Even the 3G might work, because some earlier data did this. So the application is resequencing it after the TCP socket, So this is the application side, sorry, it's the client side, this is the server side. All you do is that there's a content, let's say the video streaming, there's a scheduler that schedules these packets. Now, this actually opens two different TCP connections to the other application endpoint, and there are, and the TCP endpoint, TCP ends here, but you still have to merge these two streams. So if you don't do that at all, things can occasionally perform very poorly, because if there is some packet data you were expecting on the Wi-Fi connection that didn't arrive for some time. Okay, so that's what we call an error recovery. It's probably kind of not the right term to use. That means
so if we had some way of running just one TCP and doing the merge before the TCP, that would not be needed.
We have to merge.
Like if we just had two.
I will, okay, if just one TCP and I'm going to switch to TCP connection. So that will not happen.
Yeah.
That will not happen. But we are not doing that, because occasionally you have to strike the data on both different connections. Okay, so some of the experiments that we did, which actually eventually, perhaps like probably 2 more slides, is that we thought that what type of experiments we are going to do based on these measurements, for example. So we we thought that video streaming is sort of like an application that is going to be well received. So we streamed MPEG-4 videos. The videos are quoted at 2 megabits per second. This is a little bit on the high side. If we make it very low bitrate video, then just 3G is going to work very well. Anything might work very well. So this is on the high side. On the other hand, we didn't make it too large, because you make it really large, once again, everything can kind of might just fall apart, right? So 2 megabits per second we sort of chose because on an average the 3G was giving us about 500 kilobits per second. Wi-Fi on an average was giving us about 1500 megabits per second. So maybe 2 megabits per second sort of balances that. So we thought that may be a good thing to do. But that is the average bit rate. But the video is variable. The peak was 18 megabits per second. So sometimes you push a lot of data. Now, the way this works is that you stream this, there is a video playback on the other end. Okay, so this is the server has a scheduler. In real life, this scheduler has to be in some sort of proxy, probably. Okay. Right now, we integrate in the server. That may not happen eventually. Now, on the client side, the application sort of merges these packets, then there's a playout buffer, it buffers these frames, and then there's a playout that plays out. Now, what do we do when the frames arrive? We timestamp and log, and then we evaluate video performance offline. Now, if you want to evaluate these sort of things, because it is error-free communication at the end, right? So you cannot really evaluate any sort of SINR or that sort of stuff, because nothing is lost. So since nothing is lost, the only way to evaluate is, only thing that you can evaluate is sort of the user performance, user experience. So how do you evaluate user experience? So you model basically the playout buffer. So the way it is going to work is that this is something like a queue, and then the packets, the frames arrive. And if you start the video at this time, the frames arrive, and maybe the queue builds up to a threshold, it's a peak. And then after that, you start playing. That is the startup delay. Okay. And you start playing, and this is the buffer occupancy. It grows and shrinks depending on the rate that the frames arrive. And when it hits 0, then you really can't do anything. You have to freeze. And typically the way the video players work is that it is after the freeze, it will still expect a certain number of frames to arrive before it will start playing again. So you freeze. So there is a startup delay, there is a playback period, continuous, and there is freeze. Okay. Now user experience will depend on how late you start playing the video, right? Then how frequently you freeze. Each time you do freeze, how long the freeze period is. Okay. That will depend, of course, on the buffer. If you make the buffer very large, okay, sorry, not the buffer, the threshold very large, then the startup delay is very long. Okay. And the number of freeze instances is going to reduce because you are going to ride out small fluctuations. But the freeze time is going to increase. because the threshold is large. So we can play with this buffer. So we do not really want to say what the buffer is going to be because we are doing evaluation of the network. We evaluated this over a large, like big range of values, and this kind of obvious that if you make it larger, then the larger startup delay and longer or less frequent freezes. Okay, but either way, this is going to be bad. Small is going to be bad in one way, large is going to be bad in other ways if the network is not performing very well. And we compared so far the hybrid of 3G and Wi-Fi, okay, and 3G by itself. We probably should cover maybe other techniques here that we haven't done yet. Now, so hybrid, this hybrid is basically the technique that I sort of described using that framework and the schedule. 3G by itself is just vanilla 3G, nothing else. Now, turns out that hybrid uses a much less number of bits, almost a 3/4 reduction in number of bits, which sort of reflects the way the throughputs work in both networks in our previous measurements. On the other hand, so it is not only putting a less number of bits, but sort of obvious here from the measurements that it will give you much superior experience because we are using and I'm not showing you all the plots, but roughly 50% less startup delay, 3 to 5 times less freeze instances, and 3 to 5 times less total freeze time. So it's a much better experience for that video over a large range of this threshold. So regardless of how you set the threshold, you get a much better experience. So that is the message, and hopefully within another month or so, we'll be able to complete many other evaluations, and maybe in future, I can show you these other comparisons. So, of course, we are going to do more evaluations. This is the last slide. But as I said, the idea is for us to use SCTP so that we can actually put it on a much more industry standard, robust transport protocol. We are also trying to look at the energy angle, so not only look at the cost of the network, but also the energy expenses. And there has been a lot of work in this space recently, particularly in many of these mobile systems conferences, because the 3G and Wi-Fi, any type of network consumes different amounts of energy, has a different energy profile. And sometimes networks like 3G actually have what they call is the tail energy, because they hold on the channel longer than the packet transmit time. And that influences the energy behavior. So you can think of modeling that and putting that in similar sort of framework. Similarly, you can do other things. Here we are talking about mostly like download sort of applications, streaming sort of applications. You can think of application that wants to do transfers that's not immediate, like email sync, which can wait. Okay, so here in those cases, it can wait for until you get a very good Wi-Fi connectivity, and then only you're going to do that. Some of the work, in the literature, kind of focuses on these particular. Now, one of our interests is also to think of kind of new ecosystems. So if this idea, if you know the details, sort of seems interesting, seems useful, particularly in the context of metro Wi-Fi, because otherwise I do not see any way of this being useful. Only metro Wi-Fi can really make it a reality. And then one can think of tightly integrating the networks to make it even better. Not only the networks, but also the services. Because in some way, if the networks and the services, particularly like scheduler, sort of work together, here everything is sort of independent. If they can work together, there's potential of better performance. And that can give an incentive for providers to work together with services like this proxy, because the scheduling has to be done somewhere. Probably it's not going to be done on the web servers, because web servers are not going to be updated because of our work. But there could be proxies that could be deployed for doing some scheduling. So that is the message here, and then I can take other questions. Yes.